Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we are going to discuss finding solutions to a system of linear equations. In this topic, we will begin by describing the zero equation. We will define homogeneous linear equations. We will review the properties of linear equations. We will consider all possibilities with a single equation in one or more unknowns. We will consider issues when there are two linear equations but only one unknown. We will then solve all three cases with two linear equations and two unknowns, including a unique solution, no solution, and infinitely many solutions. We will also look at higher order systems of linear equations and foreshadow what we will be looking at in subsequent topics. Alright, to begin, the zero linear equation in n unknowns is of the form 0 times each variable summed is equal to the target value b sub 1. Now, if b sub 1 is equal to 0, then there are infinitely many solutions, as every solution vector x is a valid solution. Basically, all n variables are free. You are free to choose any values you want. If, on the other hand, the target value is not 0, then there are no solutions, because no sum of zeros will ever equal a non-zero target value. Now, from this point on, we are going to assume that when I say that we have a linear equation, then we're going to be assuming that there will be at least one non-zero coefficient of at least one of the variables. The only place where we will end up with the zero equation is when we start manipulating a system of linear equations to find a solution, if one exists. Now, definition. A linear equation that has a target value or right-hand side equal to 0 is said to be a homogeneous linear equation. All other linear equations are said to be non-homogeneous. For example, here we see a homogeneous linear equation. The right-hand side is equal to 0. If the right-hand side is changed to anything else, say 1, it is no longer a homogeneous linear equation. It is a non-homogeneous linear equation. Theorem. The n-dimensional zero vector is a solution to a linear equation with n unknowns if and only if that linear equation is homogeneous. Proof. Substituting in 0 for each of the unknowns into this linear equation, we get that the left-hand side is equal to 0. Now, if it does actually satisfy the equation, then 0 must equal b. Thus, the equation is satisfied if and only if b is equal to 0. Now, as a consequence, we immediately know that if a linear equation is homogeneous, then the zero vector is a solution, and if it is not homogeneous, the zero vector is not a solution. Theorem. A vector x is a solution to a linear equation if and only if it is a solution to a non-zero scalar multiple of that linear equation. Proof. Given x, assume that it is a solution of this equation. That is, for the values of x here, that equation holds. Both sides are equal. Consequently, if two things are equal, I can multiply both sides by any constant, and the result is still equal. On the left-hand side, I can use the distributive property and the associative property to get that, oh, this must also be true, and so therefore x must also satisfy the equation where each of the coefficients is multiplied by c. Now, going the other way, assume x satisfies this linear equation. Well, we assumed that c was not 0, and therefore c has a multiplicative inverse. So let us multiply both sides of that equation by that multiplicative inverse. Now, on the right-hand side, you can see immediately that c inverse times c is equal to 1, and 1 times b is equal to b. On the left-hand side, you can see that we can distribute c over the addition and then use the associative property of multiplication to get c inverse times c, which will equal 1. And so consequently, we can see that that equation must also be satisfied by x, and so x also satisfies the original equation. Theorem: if a vector x is a solution to two linear equations, it is also a solution to the sum of those two linear equations. Proof: given x, assume that x is a solution to these two linear equations. Consequently, substituting in the values of x, both of these equations hold. Now, if I have two equations, I can add them together. I can add the left sides together, and I can add the right sides together, and the results will be equal. The only thing now is, on the left-hand side, I'm going to group according to the x's. But wait a second now. This indicates that these x values satisfy the linear equation that is the sum of those two linear equations, and consequently the theorem is correct. Now, consider one equation and one unknown, assuming that that coefficient is not 0. In this case, there is a unique solution which is easy to find. Consider, however, one equation and n greater than 1 unknowns, where we're going to assume for now that the first coefficient is non-zero. Well, in this case, every other variable other than x1 is a free variable, and if they are all free, then from those values we can deduce the value of x1. Thus, the solution vector is as follows, and as you can see, as soon as you introduce even one free variable, you have infinitely many solutions. Now, in the odd case that the first coefficient is not 0, we assume that at least one of the coefficients is not 0, and in which case we'd probably choose the first coefficient that was not 0 and then solve that for all other values based on the other values of the unknowns. Now, suppose you had two equations but only one unknown x1. Let us assume again that the coefficients a sub 1, 1 and a sub 2, 1 are non-zero. The first equation says that x1 is equal to b1 over a1, 1, while the second says that x1 is equal to b2 over a2, 1. Now, if these two are different, no solution exists. It's sort of, as this example shows, the first equation says x1 must equal 2.5, whereas the second equation says that x1 must equal 1.75. Well, x1 cannot equal both these values simultaneously, and thus no value of x1 satisfies both equations at the same time. Now, if they are equal, that is, these ratios are the same, this can only happen if equation 1 is a scalar multiple of equation 2. Here's one such example. In the first equation, I have that x1 is equal to 2.5, and in the second, we have that, once again, x1 is equal to 2.5, and you will notice that the second equation is negative 1.5 times the first equation. We're now going to look at two equations and two unknowns, and we're going to look at three possibilities. The first one is the general case. Here we have two equations and two unknowns. From secondary school, you would have known that you should add negative 3 times equation 1 onto equation 2. That cancels out the 3x1 in the second equation. Now, the second equation has only one variable in it, and so therefore we can solve for x2. x2 is just 6 divided by negative 8, which is negative 0.75. All right, now given x2 is negative 0.75, we can substitute that back into equation 1. Well, that gives us that equation there, so x1 minus 1.5 is equal to 1. Therefore, x1 is equal to 2.5. All right, so the solution vector to this system of linear equations is the vector x equaling 2.5, negative 0.75. And this is the unique solution to this system of linear equations. Now, given a system of linear equations, a solution vector x is a solution to that system of linear equations if and only if it is also a solution vector to that same system of linear equations, but with one of the following operations performed on that system of linear equations. Multiplying any one equation by a non-zero scalar, adding a multiple of one equation onto another equation, and swapping two equations. So if two systems of linear equations are equivalent, we will denote this with a tilde. So from the previous example, we saw that these two systems of linear equations are equivalent. We may even add a note indicating what the operation was that makes them equivalent. So in this case, we added negative 3 times equation 1 onto equation 2. We're now going to look at two equations and two unknowns, and we're going to look at three possibilities. The first one is the general case. Here we have two equations and two unknowns. From secondary school, you would have known that you should add negative 3 times equation 1 onto equation 2. That cancels out the 3x1 in the second equation. Now, the second equation has only one variable in it, and so therefore we can solve for x2. x2 is just 6 divided by negative 8, which is negative 0.75. All right, now given x2 is negative 0.75, we can substitute that back into equation 1. Well, that gives us that equation there, so x1 minus 1.5 is equal to 1. Therefore, x1 is equal to 2.5. All right, so the solution vector to this system of linear equations is the vector x equaling 2.5, negative 0.75. And this is the unique solution to this system of linear equations. Now, suppose you had these two linear equations with two unknowns. Well, once again, we will try to eliminate x1 in the second equation. We will add 3 times equation 1 onto equation 2. Now, interestingly enough, this now gives us the 0 equation equated to 0. So that says that 0 times x1 plus 0 times x2 is equal to 0. Well, that's the 0 equation, and consequently, this equation no longer puts any constraints on any solution. Any values of x1 and x2 satisfy the 0 equation. Therefore, the only equation that constrains x1 and x2 is the first equation. The problem is there's one equation and two unknowns. Therefore, when we're dealing with this one remaining equation, we need a free variable. Let that free variable be x2, and therefore solving the equation for x1, we get that x1 is equal to 1 minus twice the free variable. Thus, every solution to this system of linear equations is represented by this vector x, and you can replace x2 with any real number and it will be a solution to this system of two linear equations and two unknowns. If x2 is 0, x1 is 1. If x2 is 1, x1 is negative 1. If x2 is negative 1, then x is equal to 3. And you can try it out. All of these are solutions to the above system of two linear equations and two unknowns. So, given a system of 3 linear equations in 3 unknowns that we would like to solve, we are going to apply the operations on these equations as we have described in order to eliminate variables in the subsequent equations. So, for example, suppose we started with this system of 3 linear equations and 3 unknowns. The first operation I would perform is I would add negative 0.5 times equation 1, and I'd add that onto equation 2. Similarly, I would add 1.5 times equation 1 onto equation 3. Those are acceptable operations on equations, and if you were to perform them, you would see that the first system of linear equations is equivalent to this second system of linear equations. Well, now we'd like to proceed by eliminating the next variable. So, I have 0.5 and 8.5, so I would have to add negative 17 times equation 2 onto equation 3. Doing so gives us the following system of 3 linear equations in 3 unknowns. Notice, however, we now have eliminated all but one variable in the third equation. But that makes the third equation by itself a single equation in a single unknown. So therefore we can solve for x3. So taking that equation and solving for x3, we get that x3 is equal to 0.2. Now, substituting x3 is equal to 0.2 into equation 2 gives us this equation. But this equation, once again, is just a single equation in a single unknown x2. So we can trivially solve for x2. So x2 ends up being negative 0.5. Finally, we can substitute both x3 and x2 into equation 1, which gives us this equation here. Notice now at this point, this equation has only a single variable in it, and that is x1, and we can solve for x1 to get the solution there. Thus, the solution vector is the three-dimensional vector with entries 0.3, negative 0.5, 0.2. Now, given a system of n linear equations in n unknowns, again, assuming that there's nothing special happening, we would proceed as follows. We would start by looking at the first equation, and then we would add an appropriate multiple of equation 1 onto each subsequent equation so as to eliminate x1 from every subsequent equation. All right, now if we ever added another scalar multiple of equation 1 onto any subsequent equation, we would reintroduce x1. So we don't want to use equation 1 anymore. Instead, we move on to equation 2. Now equation 2 has a non-zero coefficient in front of x2, hopefully, and if so, what we will do is we will add an appropriate scalar multiple of what's left of equation 2 onto each subsequent equation. And once again, that will eliminate x2 from every subsequent equation. Once again, if we ever again tried adding x1, equation 1 or equation 2 onto any subsequent equation, then we would be reintroducing either x1 or x2 respectively, and we don't want to do that. So instead, we would carry on with equation 3, or more correctly, what's left of it after we have eliminated the first two terms. We would then proceed to continue to do this for all subsequent equations until we are with the last equation. This last equation will then be of the form a scalar times xn is equal to a scalar, which is a single linear equation in a single unknown, which we can already solve for. Having solved for x sub n, we can then use backward substitution to find x sub n minus 1, then x sub n minus 2, all the way up to x, solving for x1. Moving forward, working with equations is tedious, and it's rather difficult to program into a computer. In fact, how could you program this into a computer? So moving forward, we will introduce the augmented matrix representation of a system of linear equations, and then we will define algorithms on that augmented matrix in order to find a solution to the system of linear equations. So, following this topic, you have now recalled some of the rules you used to solve a system of linear equations in secondary school. You know that there may be no solutions, a unique solution, or infinitely many solutions. You know that a homogeneous linear equation has a zero right-hand side. That is, the target is 0. You know that there are 3 operations you can perform on equations that leave the solution to those linear equations unchanged. And you have reviewed solving systems of 2 and 3 linear equations with as many unknowns. Here's the references, acknowledgments, the colophon, and a disclaimer. Cheers!